weeks of lecture. Yeah. So last week we talked about shadowing solutions and how they can be non-physical, and I'm just giving a reference here. So if you find your homework questions in your homework, you're welcome to ask me, and you can also find some pretty good information from the paper listed over here, right? So it's all of these papers are pretty new, so you should have access to the notebook, and if you forget, you can always come back to the OneNote and look at this paper.
So I was doing the homework, right? I thought there was something weird about shadowing solutions is that when you go backwards, you're doing the tent map and you need to know which side of the map you are.
Yeah.
So I thought it was really weird how you had to already have you're using a solution of the forward solution as you're doing your backward solution.
Right.
Does it mean it's not defined on its own or something like that?
It is, the shadowing solution is defined not on its own, right? It is defined as the solution that satisfies a particular equation, but is as close as possible to another solution that's actually not exactly the solution to the governing equation, but a pseudo solution. That's correct. It is not defined on its own, right? So like a regular solution, a forward solution obtained from an initial condition is also defined based on the governing equation and on the initial condition, right? While the shadowing solution is defined with another different way. It's defined, of course, also by the governing equation, but also by another pseudo solution.
Okay.
All right.
So it's a shadowing solution.
Yes, that's right. Okay, and what I'm going to be talking about today, you can find it from another paper. So, ergodic sensitivity analysis of one-dimensional chaotic maps. So, a lot of the ideas or explanations I'm talking on lectures, I realized in the last Wednesday's lecture, I did not explain Rail's linear response equation very well. I mean, that's because a lot of the concepts are very, very new, and we haven't really able to figure out a way to explain it perfectly clearly yet. Okay, so this is something I learned way after my PhD, was that when I was taking a lot of the advanced graduate classes during my PhD, I figured out it's really difficult to understand a lot of things that was taught in class, right, as opposed to be a more junior classes. And later on, I figured out was not because I was stupid or anything, right, because nobody has ever figured out how to explain some of the newly discovered concepts perfectly clearly yet. And it's really years later, other people was able to explain it. It may not be the person who discovered the concepts in the first place, but other people, through their own words, was able to figure out different ways and better ways to explain things more clearly. So for example, the Rail's linear response formula is discovered by David Rail, it's a French mathematician. But if you read Rail's original papers, it's really hard to understand, especially for people who are not in the field of theoretical dynamical systems. So what I have been trying to do is really to explain things in a more computational way, right? For people who are not theoretical, not pure mathematicians, but who are able to understand things computationally to understand these kind of formulas. But even though I may not be able to explain things with perfect clarity, maybe one of you will be able to figure out ways to explain things better. Okay.
All these were derived in this field, right?
What?
All these things were derived in this field, right? They weren't derived tangentially and then people applied it here. They always wanted to solve these problems.
A lot of things I'm discussing here was first derived in the field of dynamical systems, which is not a field of applied mathematics. It's a field of pure mathematics. So if you look at the papers written by people in the dynamical systems field, they are always written in terms of a manifold, the tangent spaces, and things like that, right? Even if the manifold is just a three-dimensional Euclidean space, they always write it as manifolds. All right, even if it's finite dimensional tangent space, you can really figure out a coordinate system and use a vector to explain things. Nobody in that field, it's socially unacceptable to write things in a like so like when I actually did my undergrad in pure mathematics. So when I'm learning linear algebra, like you never write a proof with a matrix in it. Okay, it's always a linear operator. So if you can explain things as a linear operator, then you're not supposed to explain things in a matrix. So that's kind of the mentality of pure mathematicians, because it's more general, right? A linear operator can easily generalize to a infinite dimensional operator, while if you have a matrix, it's always finite dimensional. So like in pure mathematicians, always think of expressing things in the most general way, as opposed to if we are doing computation, it makes much less sense, right? If it's a linear operator versus a matrix. So there is always different ways to explain things, and I'm trying to do my best to explain things clearly from a computational point of view. Okay. So last lecture we learned that long time averaged quantity, right, can be written as an integral over the phase space. And since we have been looking at a one-dimensional maps from, for example, from 0 to 1, we are integrating over the phase space of the interval from 0 to 1. Okay, and is the compound of the objective function itself with the map. And now we are parameterizing the map with the parameter s, right, over n iterations. So this is the objective function after n iterations, and integrated with the ergodic measure, right? And this ergodic measure does not have to be the ergodic measure with the parameter s. It can be the ergodic measure with the parameter 0 if my n goes to infinity. So this is basically saying that if I start from the ergodic measure with a different distribution, when I look at the objective function after n iterations, and n is very large, then the objective function, even though I'm using a slightly wrong distribution, but after I evolve for n iterations, the slightly wrong distribution would actually converge to the correct distribution. And so if I look at the objective function n iterations later, right, I do have the correct long time average with respect to the parameter s. Right? Does that make sense? So the Ruel's formula is really starting from this and differentiating this compound function with respect to the parameter s. So we may not be, I mean, since of course we know how to differentiate the compound function with two compounds, right? A function f, a function g. But we may not be familiar, maybe none of you have ever did a chain rule with respect to a very, very long, arbitrarily long compound function, right? So it's really j compound with phi, compound with phi again, compound, etc., compound with phi, right? There are n such compounds. How do we differentiate such a compound function? Well, if you know like the basics of differential calculus, you should know that when I have n plus 1 functions compound with each other, and n of them are functions of s, right? This derivative can be written as a sum of n components. Each component is the result of perturbing only one of these functions that depend on s, right? You can just think of these as n functions, each of them depend on s, and the total derivative should be the summation of perturbing just one of them and add it together. Okay, so it is really the sum of, let's say, I goes from 1 to n, and let's say this is, if I perturb this function, it's I equal to 1. And if I perturb this function, is I equal to n. So I'm adding up the result of perturbing each function in the chain individually. Okay, so for example, what is the result of perturbing this function? What is I equal to 1? So let me just maybe before writing the sum, I'm just going to write the contribution from I equal to 1, I equal to 2, and etc. to I equal to n individually. Okay, when I'm perturbing just this function, and this is assuming all the other functions, all the other n minus 1 functions are fixed, not considering how these functions be perturbed by s. And I'm only perturbing this. What is the result? The result is basically compounding two functions. The result is dds of, let me just write it down. The first component is the derivative j compound with vs for n minus 1 times. So this is this part of the non-perturbed part. Okay, its derivative as a function of the independent parameter, not s, as a function of s, and evaluated at vs of x, and times the derivative of vs. Right? This is the function that gets perturbed. This is the function that did not get perturbed. So this is the I equal to 1 perturbing the last function in the chain. Okay, make sense? Okay, I equal to 2 case would be fixing two parts. I equal to 2, I'm fixing the first n minus 2 vs's and the last vs. I'm perturbing the second last vs. So this is, I'm going to be adding j compound with vs n minus 2 derivative. But that's evaluated at vs squared x, right? And then I'm perturbing the derivative at vs, but that's evaluated, I mean, this one is evaluated at x, but that perturbation, because I'm fixing the last one, is evaluated at vx of x. All right, make sense? Okay, so this is basically looking at the perturbation due to the last feed depending on s and the second last feed depending on s, and etc. Right, goes all the way to add all the way to the last one. The last one is basically perturbing the last vs, right? So that's just the j derivative, but operated on evaluated at feed to the nth power x, and then times the perturbing function, right? The n function in the chain, but evaluated at vs n minus 1 x. So this is basically we are applying chain rule to a compound function with n plus 1 functions compounded with each other, and n of these functions depends on s. All right. So now if we write them together, if we write it as a summation, figure out what is the rule, right? I equal to 1 to n. We are going to find out that the first component is j compound with vs to the power of n minus I, right? The derivative of that. So when I is equal to n, vs to the 0th power means there is no vs, it's just the j prime, okay, the derivative of j. Times, but this is evaluated at phi to the I minus 1th power x. So that's the location where the derivative is evaluated. And then times the derivative, the partial derivative of phi with respect to s, but then evaluated at vs oh, sorry, this is actually not I minus 1, this is I. So yeah, so the derivative is evaluated at the ith compound. The partial derivative of phi is evaluated at I minus 1th power of x. Right, so that's the result of the chain rule. And once we plug the chain rule into the integral, there is another thing we can use. That's the integral is integrated over the ergodic measure, the equilibrium measure, over x. And because of the equilibrium measure, right? So when we are taking derivative, we are taking derivative at s equal to 0. Right, at s equal to 0. So we just write this as 0. Okay, and therefore, so basically at s equal to 0. Okay, therefore, when we integrate it, it doesn't matter if we are integrating over the ergodic measure of x or the ergodic measure of phi to the I minus 1x. Right, because the probability density function over the interval of x is the same as the probability density function of phi x, and is the same as the probability density function of phi square x, right? If we take the ensemble, map it for no matter how many times, it's the same distribution. So the integral over them, the integral of dds j compound with phi to the nth power and d rho x is equal to, when we substitute, let's first do the substitution, right? I equal to 1 to n. We can always change a finite summation with the integral. And j compound with phi to the n minus ith power prime. So take the derivative of a future objective function, right? Evaluated at phi to the ix times the derivative of the partial derivative of phi with respect to s, evaluated at phi I minus 1x d rho x. So it doesn't matter if this is d rho x or if this is d rho of phi I minus 1x, right? And as a result of that, we can just change a variable. We can just call phi I minus 1x as x, or as 1. All right? And therefore, this function evaluated at phi to the ix is equal to, so let's just say this is, we just call this as y. Okay? And if we call this y, then this is y, and this is phi of y, right? Because y is phi to the I minus 1, right? So phi to the I is phi operated on y. Okay, so then what we get is this summation. I goes from 1 to n. Integral. Still, the derivative is still the same, but operated at phi y times now the partial derivative of phi s at just the y and the d rho of y. Now, of course, it doesn't matter what I call the index, right? The index I goes from 1 to n, which means this n minus I goes from n minus 1 all the way back to 0. So I can, of course, define the index with differently. So let's say j, let's say define as n minus I, right? Then j would go from 0 all the way to n minus 1. I would have an integral of j. This is small j, right? A big J is the objective function. Phi to the power of small j prime evaluated phi of y, and the times the same thing. And remember, this would be exact when n goes to infinity, right? So basically, if we replace the n minus 1 with infinity, we get the Ruel's linear response equation. Okay, and so this is a general equation, while the map phi may or may not be invertible. So for our sawtooth map, phi is not invertible, and this is correct. In the case that phi is invertible, many people write the Ruel's linear response formula by instead of defining y being phi to the I minus 1 x, we can also substitute y equal to phi to the ix. And in that case, right, we need the phi to be invertible. This is going to be exactly y, and this is going to be phi to the minus 1 y, right? In that case, people just write, okay, a j compound with phi to the jth power prime evaluated at y, and then dds of vs, but now evaluated at phi to the inverse, like the pre-image of y. So that's also another way to, in the literature, you can actually see a lot of, you see more of that formula, right, based on where the partial derivative, the perturbation, is evaluated at the pre-image of y. Of course, that assumes the map is invertible. All right. Okay, any questions on this? I hope this is a more easier way to understand how the Ruel's formula was derived. Okay, it's basically taking chain rule and use the fact that the equilibrium measure, the ergodic measure, is invariant under the transform. So we do a change of variable based on that, and then do another change of the index, and take n to infinity. That's the formula. Okay. Now the next thing we want to figure out is why the Ruel's formula is incredibly difficult to evaluate just on the face of it. And that requires us to understand the first term, the derivative of the objective function evaluated at a location after j iterates. Okay, so let's actually understand a little bit of what that derivative is by first understanding that compound function, j compound with phi to the jth power, what that looks like. So let's go back to our IPython notebook and just using the standard, I think do we have an objective function? We don't, right? So let's take an objective function j, okay? That's equal to a function that's high in the middle and low at the two ends. So let's take actually low in the middle, high at the two ends. So let's do cosine of 2 times x, right? So x is equal to just the link space 0 pi. That's from pi lab import all. Okay, 0 to pi, and let's just give it 1,000 points. J equal to that. Of course, if we plot x versus j, we get our cosine-like function, right? Now what we want to figure out is, so that's the j. Now let's figure out what is j compound with phi, and assuming phi is the sawtooth map. Okay, so for that, what we want to compute is x would be equal to, let's say, x1 is equal to 2 times x modulus pi. And now let's plot j compound with the function once is equal to cosine of 2 times x1, right? And now let's plot x versus j1 and see what that looks like. Well, the orange curve is what the compound of our objective function with the map once looks like. It makes sense, right? So, for example, the original j is the lowest in the middle, but the j compound with the function 1, with the map once, is lowest at two places, right? Because if my j is at, if my x is at now a quarter pi or 3/4 pi, my phi of x is gonna be at half of pi, right? Remember what the sawtooth function looks like? It looks like my sawtooth function looks like that, right? Okay, so if the objective function is the lowest over here, then if my x is here or here, then after one map, I get to this point, the middle of the domain, and my objective function would be lowest. So there are two locations. I'm basically repeating the objective function twice, but squeezing the x-axis a little bit more, right? Okay, then what is my j compound with phi twice? Now let's say x2 would be, again, using the same formula, but to x1, right? Just applying the map another time. So j2 would be cosine of 2 times x2. And if we plot x and j2, we get the green curve. So the green curve is essentially the blue curve, the original function, but repeated 4 times as opposed to twice. Okay, and we can keep going, and we can say, okay, what do you think is what do you think j3 is going to be looking like? Anybody wants to take an imagination? Well, 8 times, right? So basically, you can think about the j compound with the map for I times being the function j repeated over the domain for 2 to the j times, right? So that is saying that when we look at this term in Royle's formula, j compound with phi to many times, this function, when j is small, is a smooth function. And the larger the j is, the more oscillatory that function is, right? And it's getting more and more oscillatory at the exponential rate, okay? Which means something pretty significant to the derivative of that function. If you look at the derivative of the blue function, oh, it's nice. The green function, the red function is becoming bigger and bigger, right? The derivative explodes exponentially. That means in this integral, the integrand, because of the first term, the integrand actually would become very, very large. Now, one thing to be careful, it doesn't mean the integral become very, very large, right? Because the integral is actually integrating over the very oscillatory function. So even though the derivative is very large, the negative derivative and positive derivative kind of cancels out, right? If you integrate the product of that the derivative of the oscillator function with a smooth function, the product after integration, the positive and negative cancels out. So the integral may not be very large. Actually, the integral we actually figured out last time, I think from this example, right? The integral actually does not increase exponentially. The integral actually converges to 0, right? So the sum of the series, when the series is the integral, actually converges, but the integrand grows exponentially. So that's the fundamental problem about evaluating Royle's formula according just to the formula itself. All right, make sense? So now let's look at how can we make this formula easier to evaluate or remove the problem about the exponential growth of that integrand. Oh, something? What?
Not ours. Just
Okay. So the fundamental problem is because we are taking the derivative of a very oscillatory function. So can we get the derivative out of this function? Right? Remember, like this integral is integrating the derivative of an oscillatory function. It integrates to something small, but the integrand is very large. So there is, in calculus, there is always the possibility of integrating by parts, right? So if the derivative operates on the oscillatory function, we can always move the derivative to the other component of the product so that we don't have to take derivative to this very oscillatory function. Okay, so of course, if you look at this formula, it is not obvious how we do the derivative immediately, so we still need to take some transformation to this function. And this also, the motivation for integration by parts also tells you why, in the case of an invertible map, right, it is often easier to define y not as phi I minus 1 of x, but phi to the I of x, so that this term, which we want to take the derivative out of, is exactly evaluated at y, so it's going to be easier. But for our case, for the non-invertible map, I want to introduce a transformation, which is really a divide and conquer strategy that is going to be also useful when we are talking about cases where there are stable and unstable components in the chaotic dynamics. So this is still, we are looking at the case with a purely unstable dynamics, right? And we'll see later what difficulty we encounter when we have both stable and unstable directions, and how to use the same divide and conquer strategy to deal with that. So let's first rewrite Ruel's formula here. DDSJ is equal to summation of let me still use the index I, because I don't want to confuse with the J here. From 0 to infinity, right, as we take n goes to infinity. So the summation goes all the way to infinity. Integral over the domain. We have J compound with phi to the ith power, evaluated at phi x, and then times, so this is not times, this is evaluated, this is times the perturbation in the map. So changing the map itself, right? If we are perturbing the map to something like this, for example, then the DDS is this function, right? Is the function that is the partial derivative of the map itself with respect to the parameter while holding x to be fixed, right? Phi at x d rho x. Okay. And let's just define one of the terms as as dj bar I. Okay, so let's just focus on the dj bar I. Okay, so dj bar I, the ith component in the infinite series, can be written in two parts. So here we are taking a divide and conquer strategy, right? So because when you think about I'm integrating x from 0 to 1, how does the independent variable of, sorry, I have a derivative. How does the independent variable of this function change? Right, phi x would go from 0 to 1 and then go back from 0 to 1 again. So I want to split the integral into two parts, okay, so that I can do a change of variable easily. So I'm going to be integrating from 0, x goes from 0 to half. So that's the first time the phi of x goes from 1 to 0 to 1. Sorry. Excuse me. So Okay, so d row x plus x goes from half to 1, right, of the same thing. Now, in each of the integral, now I can do a proper change of variable. I can call now this as my new y, right? Okay, and of course the y then goes from 0 to 1 again in both cases, right? In both cases, I can take the preimage of, I can take the image of x after one map to be y, and in both cases y goes from 0 to 1. So this is j compound with phi to the ith time at y, and now this is dds of phi evaluated at the phi inverse, let's say the left half, right, of y times d row. So this is again at phi left inverse at y. All right, and then I plus the same thing, but this is the same thing but evaluated at the right branch, and this is evaluated at the right branch. All right, so I'm dividing the thing into dividing the whole domain into two parts. So each part I do have a inverse function. Now I can really start the integration by parts, right? I can move the derivative to the other parts of the function. So let's consider actually starting from the easier case. Let's start from the case where row, let's start with row being uniform. Okay, the equilibrium density is equal to 1 everywhere. So this is the case when we have an unperturbed sawtooth map, right? And for the unperturbed tent map, you also have row equal to 1. And so this is the easier case, and we'll further later on consider there is an additional term comes into play when row is not equal to 1. Okay?
So, like for general systems, is it usually uniform? Like we're looking at.
It is not. It is not. So in the general system, we have this additional term, but like let's derive one term by one term. And like after each derivation, I'm gonna show you physically what that actually means. All right. So it'll be.
The distribution was like a Gaussian. We're taking like the zeroth moment of the Taylor expansion kind of thing right now.
Right. Yeah. So. Okay, so let's figure out because integration by parts is easy, right? When so the density d row of x is just equal to dx. So d row of x is just equal to dx, right? In the case. Okay, and d row of phi inverse of y, right, is equal to actually so I'm changing y by that much, x would change at a smaller rate, right? So it's actually going to be equal to dy divided by the derivative of phi at the preimage. In this case, in the case that we have the unperturbed sawtooth map in the green case, then this is going to be exactly at dy over 2, right? So basically, if you are changing y, this is dy, right? If you map with the original map, the dx is going to be exactly half of dy. And in general, dx is equal to dy divided by the slope of that map at the x location. Okay? All right. So now let's figure out in the case of, let's actually just think about the specific case where we have the unperturbed sawtooth map. And then what happens is that the left branch is just equal to y over 2, right? The right branch is just equal to y plus 1 over 2, right? On the left branch, y is equal to 2x. On the right branch, y is equal to 2x minus 1. Right, yeah, okay. All right, so then in this case, dj bar, the ith component, is equal to the two integrals. The first integral is j compound with phi to the ith power at y times the perturbation itself at half y, right? So the preimage on the left part. And again, the d rho is just equal to dy over 2. Okay? And plus the second component, again, integration from 0 to 1 times dds, but phi evaluated at y plus 1 over 2. Again, we have dy over 2. So that's that formula. Oh, prime. This is the derivative. And that's ready for integration by parts, right? Ready for integration by parts. So integration by parts has two components. One is the boundary term and one is the interior term. Okay, and again, let's just consider the easier case where the boundary term vanishes. When, let's say, when we are perturbing the sawtooth map like that, the boundary term, which is when x is equal to 0, x is equal to half, and x is equal to 1, has 0 perturbation. So that then the boundary term vanishes. So assuming phi equal to 0 at 0, half, and 1, right? If that's the case, then we get a negative sign in the integration by parts, and the troubling term, that is j compound with the map for ith time, now gets out of the integral, right? Now it gets out of the derivative, not the integral. And the other part gets into the derivative. So this is the d dy. And let me just write partial, right? Because now partial square, partial y, partial s of phi at actually I still have to apply chain rule, right? Because I'm taking derivative to y, and inside of the phi there is a half of y. So let me just write it like that. So partial s of phi prime y over 2, and there is a half coming out of this because of the chain rule, right? The independent variable is a half of y times dy over 2. All right. Is it clear that integration by parts works? Okay. And then the other term is exactly the same, but the this part is different. Y plus 1 over 2 and dy over 2. Okay, so now let's consider what we have achieved here. This function is this increasingly oscillatory function we are looking at here, right? And now this function is no longer inside the derivative, which means we still have to evaluate that function, but then that function is going to be bounded, in this case between minus one and 1, right? So it's no matter what bound bounds j, the same bound would bound j compound with phi to the ith power. So the first part is no longer the term that grows exponentially when j becomes larger and larger, when I becomes larger and larger, right? How about the second term? Well, the second term does not depend on I, right? The second term does not depend on I to start with. So no matter how big I is, the second term is the same. So again, it is not growing larger and larger as I grows. So basically, by doing this integration by parts, we have removed the integrand that exponentially grows while keeping the integral to be exactly the same. So what does that mean? That means I no longer need exponentially many samples, right? If I evaluate the integral using a Monte Carlo way by taking samples, usually how we take samples on the equilibrium measure, right? We take samples on the equilibrium measure by just following a very long trajectory and time averaging. So we would no longer need either exponentially many samples or exponentially long time average in order to be able to compute the ith component of this Rails formula to a fixed accuracy. Okay, so let's actually code this up to see if we can compute something interesting. All right. All right, so first of all, we have the j evaluated at some time later, right? And then we have the derivative of, okay, so before we actually go to the computer, let's actually illustrate. I forgot to illustrate what this actually means. What this means is quite interesting. We are taking the derivative of the map with respect to two things. One is with respect to S, and another is with respect to the spatial coordinate. So let's look at for the sawtooth map itself and visualize what that term actually means. So suppose we are perturbing the map upwards on the left branch and downward on the right branch. So this is the result of increasing S from 0 to some finite value, right? We are talking about phi of x equal to 2x mod 1 plus s times a sine function 2 pi x, right? Or this is the case from 0 to 1. If it goes from 0 to pi, it would be 2x mod pi plus s times sine of 2x. Okay. Then what is partial s partial phi? Partial s partial phi is the space between the green line and the purple line, right? That is partial s partial phi, right? So if we draw partial s partial phi partial s is this thing. And now what is the derivative of partial phi partial s? The derivative is or it doesn't matter because it's all partial derivative. You can take the prime inside or outside. Okay, the derivative is positive over here, it's 0 here, it's negative over here. The derivative is like this. So what does it mean? It means that when I'm perturbing the function so that the slope is getting bigger, okay, this is positive. This term appearing here is whether I'm making the slope of the map to be bigger or smaller. If I'm making the slope to be bigger, this term is positive. If I'm making the slope to be smaller, this term is negative. And let's think about why it matters to the long time average of the objective function. If I'm making the slope bigger, for example, over here, right? This term is positive. Then for the same dx, I'm increasing or decreasing the range of dy mapped into by the same range in x. I'm increasing, right, the range of y mapped. And therefore, am I increasing or decreasing the density of that location in Y? What do you think?
Yeah, if you're speeding up the derivative, you're spreading it out.
I'm spreading it out, right? So I'm decreasing the density, right? Since I'm decreasing the density at that location, okay? Therefore, it has a negative contribution to the objective function at that location and its future objective functions. Right? So if I'm decreasing the density here, it'll also decrease the density of after two maps, I'm also decreasing the density over there, right? I'm also decreasing the density at y and phi of y and phi square of y, etc. There is a chain of events that decreasing the density of all the subsequent mapped locations. Therefore, it has an impact on the objective function at all subsequent locations. On the other hand, if I'm decreasing the slope, like over here, I'm mapping the same dx to a smaller range of dy, right? And as a result, I'm going to be increasing the density. So if that location has a large j, then I would be increasing the objective function. And think about what this whole thing, the whole perturbation is doing. It is essentially decreasing the density on the lower half of the y range and increasing the density at the upper half of the y range. So this actually is moving some of the mass from this range into that range. Okay, wherever the mass is increased, right, with a slower derivative, it will look up if the objective function is large or small. If I'm moving the mass from a lower objective function area to a higher objective function area, it positively contributes to the objective function, averaged. If I'm moving mass from high objective function area to low objective function area, it's decreasing the averaged objective function.
One thing that I didn't understand for the second part, they don't cancel each other?
Yeah, very good point. So if the second part is like that, okay, it has exactly the opposite effect. Exactly the opposite effect. So it is increasing the density over here as opposed to decrease, right? And it is decreasing the density here as opposed to increase. So these two branches actually has the opposite effect, and they would cancel each other. So if you actually look at these two terms, right, this is exactly the same. Okay, and for this particular function, right, if you look at this, so this is d phi ds, and I'm basically evaluating at y over 2 and y plus 1 over 2. So I'm going to be evaluating this at this location and this location, which cancels each other. This location and this location cancels each other, right? So basically, if you add these two terms together, this plus this would actually exactly cancel each other. So no matter what objective function I'm looking at here, this would actually be 0. Okay, so that is actually why, I don't know if you probably not remember anymore, but we were looking at, yeah, so we did this before, and if we use a multiply by 2 as opposed to multiply by 4, I think we might take a while to run this. So this is the exactly the type of perturbation we were looking at, we were analyzing. That's it cancels out, right? What am I doing? Twice the tensor doesn't have a rand. Oh, I probably. does. Okay, yeah. So basically, you can see that yeah, this is what the case we are looking at. And first of all, you notice the range in the density is very close to 1, right? And then when we make different perturbations, you can see the smaller perturbations are here, red and orange. They are very close to green. And the bigger perturbations, blue and purple, they almost quadruple the amount of difference, right? So basically, what I'm showing here is that the density, the resulting perturbation in the density is a quadratic function of the perturbation. Okay, what that means is that the linear component is 0. Okay, the first derivative, as we can show from a transformation of Raoult's formula, the first derivative of the density is exactly 0. As a result, for any objective function, right, the first derivative of the time average of the objective function to the parameter in this case is going to be exactly 0. And the case is different if you make it 4, right? If you make it 4, let's actually take a look at what happens if we make it 4. So if we make it 4, I'm going to use blue. I'm going to use black. So the perturbation is going to be like that, right? And as you can see, then the two branches actually reinforce each other. I mean, they're actually the same as opposed to be opposite. So if you take the derivative of the black function, which is something like this, the derivative would be positive here, but also positive here, right? So these two terms actually are exactly the same. So they double. It's just doubled. All right. And that's why when you do the calculation, you're gonna see it's clearly like there is a first order component. So the amount of perturbation is not quadratic to the magnitude, but of course there is a quadratic component, right? You can see clearly from here, but there is also a linear component. So let's see if we can mathematically compute this linear component.
I have a quick question.
Yes?
Like, is there any way to do this that's like agnostic to like the model of your perturbation? Because it seems like it's all dependent on what your perturbation looks like when you get out.
Yes, so the algorithm itself is agnostic to what the perturbation is,
Like,
but the input to the algorithm is different, right? So the input to the algorithm is going to have this as a part of it. It's going to have the basically the derivative, the spatial derivative of that perturbation. So if you are perturbing as a sine of 2 pi x, you get one input. A sine of 4 pi x, you get some different input. We're going to see that this algorithm is actually going to be able to compute that, and the only difference is what input you give to the algorithm.
Because I was thinking like an airplane perturbation, like something messy.
Yeah. You should be able to compute exactly what that perturbation is as a function of. Actually, you can't just compute what that perturbation is. You have to compute what is the derivative of that perturbation, right? So you may have to do some derivation, but then the result of the derivation is going to feed into this algorithm, and you should be able to compute it. All right, so going to our OneNote. So we are going to be following this algorithm, and for computing the dj bar for each I, okay? And for I equal to 0, this is pretty trivial, right? So let's say if I equal to 0, and then we're going to generalize the code to compute like different i's. So we are first going to evaluate the input, the derivative of this this phi, right? So in our first case, let's say the d phi dvs dx is going to be equal to, what is it, s times cosine of in our code, because we always set the range to 0 to pi, right? So or Vx is equal to 2x percentage pi plus s times sine of 2x. And we are also going to consider 4x. Okay, so let's first do the purple case 2x. And for 2x, the derivative to s is sine of 2x, and then take another derivative to x, we get 2 times cosine of 2x. Okay, right? And then this is going to be evaluated at x, which is going to be basically the pre-image of y, right? Another thing you can do is that you can then compute y is going to be 2 times x modular pi, so that's my y, and this is going to be evaluated at y, right? So basically then for j in range I, yj is going to be equal to, let's say, yeah, I'm basically going to be applying this map for I times. So I'm going to be start with a, yeah, I'm just going to say this is equal to 2 y percentage pi. So that's basically applying the map for I times and evaluate the j, right? Jy is equal to so our objective function, I think, is a cosine of 2 y. So jy is equal to cosine of 2y. All right. So that's evaluating the first half, and the second half is going to be, so the second half is going to be the perturbation itself is going to be is this, and then we have to divide this by 2 and multiply by half of dy, right? Okay, so half of, so basically dy is going to be we can always write this as half of integral over the equilibrium measure, and the equilibrium measure can always be sampled, right? So what we can do is really take a random sample of x following a long trajectory, and for every x we are going to be computing the integrand, and instead of averaging between 0 and 1, we average over that very long trajectory. Okay, so that's what we are going to do. We are going to be basically wrap a time loop upon this where x follows the trajectory. Okay, so this is my jy, and going to be taking a quarter of this thing. So contribution is going to be jy times dvs dx divided by 4, right? So that's the left part of the contribution. Okay, and the right part of the contribution is exactly the same, but essentially for every y, there is a half of the trajectories come from the left end, there is half of the trajectories come from the right end. So instead of having to add them up independently, what I'm going to do is I'm just going to follow a long trajectory. So for this y, there is a half of the y's. For the same y, there is half of them coming from the left, half of them coming from the right. And the result of that is that by averaging the contribution, I already have taken account of this the summation. So basically what I'm going to be doing is that the sum of these two components divided by 2 is the average, right? So one of the divide by 2 is already taken care of. So I only need to divide by 2 to actually get the contribution. Okay, and samples plus equal to 1. So contribution is plus equal to this, right? So I'm going to set the contribution to 0, samples to 0 to start with, and x equal to random.rand, and for step in range long step, I'm gonna be computing this, and at the end I'm going to see contribution divided by samples is this dji is equal to that. Okay, and x. Okay, so let's actually look at the I equal to 0 contribution and see what happens when we make the steps larger and larger. So with a smaller number of steps, we get 0.27. With 10 times many, we get a smaller number with actually, 1 second, why doesn't it not go back to 0? Just do a little bit more samples to see what we are going to get. So what I expect to get is that the contribution should become the total, the DGI should get smaller and smaller for this particular objective function. The reason is that this loop wouldn't happen, right? Because I is equal to 0. So I'm just looking at really the correlation between j compound with phi to the 0th power. So j and phi prime, but at the pre-image of 1. Okay, and both the two terms are cosine of 2x and cosine of 2y. So if you plot what is cosine of 2x and cosine of 2y, let me actually do it over here. So if x is equal to length space of 0 to pi, and if you plot cosine of 2x, and you also plot cosine of 2y, so y is equal to that. You should see that they are exactly decorrelated in the sense that the integral of their product should be equal to 0, right? So if you plot x cosine 2x times cosine 2y, you should get the green function, which actually sums up to pretty much 0. So don't know, do I have any bug over here that so here I'm integrating jy is cosine of 2y, right? d phi s dx here is cosine of 2x, and I'm just averaging a bunch of samples, and I should get 0 if I average over enough samples.
You're not really moving x, right?
Oh yeah, that's what I'm thank you. That's what I'm missing, right? So when my samples goes 1, I need to iterate for x for 2 times x percentage pi. Yeah, then I should get basically a smaller and smaller quantity as I take more and more steps. All right. So so then I get a very small x. And same thing when I take I to be larger, I should also get a small quantity, because for example, if I take the same loop over here, if I take the same loop over here, if I map it once, what I get is the orange function, and when I multiply them, I get the green function. Again, should be exactly decorrelated, right? So decorrelated means if I take their correlation, the correlation should be 0. And if I make it 10, it should be the same, right? Again, the green function should average to 0. Okay. So what happens is that if I take I equal to 10, again, I should get a very small quantity. So this is different if I make the perturbation to, instead of a 2x, if I make it 4x. So if I make it 4x, the d phi x, so the derivative of the perturbation, which is sine of 4x to x, would be 4 times cosine of 4x. So if I make that modification, 4 times cosine of 4x, right? That's the only perturbation, and that's the only difference. The input is different. Then when I is equal to 0, I should not get a small number, but actually get the resulting perturbation, right? It's pretty much equal to 1, right? And what's interesting in this case is that for the subsequent iterations, it's actually equal to 0. That may not be easy to see, but like you can look at it from here. So if in this case y is equal to let me say go from 0, so 4y, not 4y, y is still the same, but this is cosine of 4x. Okay, what you see is that 1 second, cosine of 4x. So let me just comment this for now. So what you see is that the two functions, the cosine of 4x and the cosine of 2y, are actually exactly the same, right? If you plot their product, no, 4x and 2y. Sorry. If you product of 4x and 2y, you are getting a strictly positive function. So that has finite contribution. But if you start from, if you take I is equal to 1, etc., then it starts to become decorrelated. Okay, so basically the objective function, the future objective function, become more and more oscillatory, and when it gets oscillatory enough, the correlation between that very oscillatory function with any smooth function should be 0, right? So that's the nice thing about the Rails formula. Basically, the bigger I you get, the more decorrelation you get, and the smaller the integral is going to become. Okay, so this basically illustrates our equation. So when I is equal to, remember, like the total derivative to the time average the quantity is the summation over all i's. Okay, so in the case of our 4 cosine of our sine 4x perturbation, the I equal to 0 has a contribution that's equal to 1, right? And the I equal to 1, 2, 3, etc. all has a contribution that's negligible compared to that quantity. So the derivative of the objective function, if you look at the objective function being cosine, right? So let's actually compute it. Let's actually not just plot it. Let's also don't just compute a histogram. Let's also compute a j is equal to blank, and not only I'm adding on the histogram, I'm also adding actually torch.zeros, just the length of s, and I'm saying j of j would be plus equal to my xj. Now I'm going to be taking the cosine of 2 times xj as my objective function, right? And then my j is going to be equal to j.cpu.numpy, and again divided by n, and divided by 100, which is the number of time steps. Now this doesn't have the multiply by 1000 because it's not a histogram. Okay, then I'm going to be take another figure and plot s and j. Let's look at my torch.cosine, and I also need to dot sum, right? All tensors to be on the same device. Okay, so j needs to be also put onto CUDA for this to work. So we should be able to compute the derivative of the function, objective function, as a function of the parameter. So if you look at the slope, the x-axis goes over a range of 0.2. The y-axis, if you look at over here, almost also goes over a range of 2, right? From here to here is 2. So the derivative is about -1. And if you look at, don't forget the minus sign over here, right? So what we have computed in the formula here is contribution plus equal to just the product between these two terms. And if we take an additional minus sign, actually we should actually put a minus sign here, right? We should get a derivative that's about -1. So that's essentially an illustration of the much better way of evaluating the Rails formula. If you remember, like previously, we used the ensemble method of evaluating the Rails formula, and the more terms we go, right, the bigger error we get. And even if we use the 10 million terms, as we are evaluating like about the 10th term, we get ridiculously large numbers. While in this case, we can take I equal to 10 with no problem at all. We should be evaluating something that's going to be close to 0. While here we are just taking a million samples, right? In the ensemble sensitivity case, we get a number that's very large, and in this case, the exact value is 0, and we get 3 digits of 0. All right. Okay. So this lecture basically summarizes what we do to the Rails formula to make it much easier to evaluate. But we have been talking about the simplest case, which is the case that the equilibrium density is exactly uniform. Okay. In the case of non-uniform equilibrium density, there is an additional term that's going to come out, and we're going to be discussing how to evaluate that additional term next lecture. Just to give you a preview, the additional terms come out when we are integrating by parts. So we want to take this term, the very oscillatory function, out of the derivative. And the result of that is the rest of the terms are going to be taken into the derivative. And in case when the density is non-uniform, the rest of the term is actually the product of what we already have with the density itself, with the rho, right? So as a result, the derivative has to be applied after integration by parts, not just to this part, right? But also to the product of the perturbation and the density. As a result of that, there is a second term coming out of the integration by parts that involves the magnitude of the perturbation, not its derivative, but also the density, not the density, but the derivative of the density. So in terms of this figure, you can imagine the perturbation. Let's imagine the purple one is the perturbation. The perturbation actually would change the density here in two ways. One way is the derivative of that perturbation is going to make the density larger or smaller. The second part is that it is going to, instead of mapping the density from this dx, it will map the density from a different dx. Right? This shift in the location of this mapping doesn't matter if the original density is uniform. But if the density here is different from the density here, then the magnitude of the perturbation actually matters, right? So if the magnitude, even though if you look at this point where the derivative has no change, but if it moves the location from which the density is mapped, and the density is non-uniform, then there is going to be another term. So that'll leave to the Wednesday lecture to discuss that part. All right, so see you on Wednesday to really complete our discussion of what is the computationally feasible way of analyzing the parametric sensitivity of chaotic systems. Okay, see you Wednesday. And if you have questions, I'm here to answer.